Hello and welcome to lesson number 4 in Unit 7, Exponential Functions in our grade 11 University College math class. This is the last lesson of Unit 7. Typically we accompany this content in lessons with an assignment that we do in Excel or in Google Sheets. It fulfills more of the requirements for the specialist high skills major, for which this unit sort of represents the requirement. And yeah, let's get to the lesson. So properties of exponential functions is how we're going to finish. And just to sort of set it up here a little bit, exponential functions is kind of the big new concept that we tackle in grade 11. In grade 9 we get linear relations or linear systems, and then in grade 10 you get quadratics, and then in grade 11 you get exponential functions. That's kind of the third sort of broad category of function that we look at. This is accompanied by Unit 6 in our course, which is Exponent Laws, and Unit 8, which is Financial Applications of Exponential Functions. So today's lesson is about how do we recognize an exponential function when compared with the other types of functions we've encountered over our high school math career. We're also going to look at some of the characteristics of exponential functions with respect to their graph and some of the key features we've been looking at in terms of functions over the semester. So let's jump in. First thing I'd like you to do is hit pause on the video and sketch out these three graphs, which are represented by the three tables you see below. F at x equals 2x, g at x equals 3x, and h at x equals 1/2 x. So take a second, pause, copy this down either into your note or onto a blank sheet of paper, and then we'll start filling out the table below this as we talk about them. So do that now. Okay, you're back. Let's start by, first thing I want to do is just have a quick gander at the function. So we're going to start with f at x equals 2 to the exponent x. So that's the purple one right here. Now what do we notice about this particular function? Well, we notice that it's, I'm going to grab purple here. What we notice is that it has a y-intercept at 1, as do all of the functions that we graphed. In terms of these points, what you see here is this increase, and it heads sort of up. There's a little arrow on the end to show that that's going to continue. And then the same thing in the negative side, we're heading this way. Now what I'd like to point out about these points, which are down here in this table, is that outside of the y-intercept, you're going to start to see a pattern emerging, where you've got 2 and 1 over 2, and 4 and 1 over 4. That's a pattern that you're going to see continuing in the other functions, the other exponential functions that we've been graphing. So let's consider the domain of this function. So again, we're looking at the purple one here. Remember, this thing's going to head off in this direction forever. It's going to keep going up. So the points were 2, 4, it will then be 8, 16, 32, 64, etc. And then as we head off in this direction, it'll be 1/2, 1/4, 1/8, 1/16, 1/32, etc. And again, that pattern's going to go on and on forever and ever and ever. So that tells us that our domain, as we see down here, is going to be wide open. So to write it out in set notation, the set of all x, such that x is an element of real numbers, no limits. It's going to head out in both directions forever. And our range, on the other hand, is a little bit different. It does have a limit. So let's consider the range. Remember that as our function heads off to sort of what I would call positive infinity, so positive x values to infinity, that number is just going to keep growing. And the number that it's going to approach is actually going to be infinity. Because like I said, it goes 2, 4, 8, 16, 32, 64, 128, 256, etc. It's going to just continue to double, and that's going to head up to infinity. But what's interesting is as we head off in the negative direction here, we get 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. These pieces keep getting smaller and smaller and smaller. But if we think about it, will this function ever actually reach 0? No, because we'll always be able to sort of cleave it in half a second time and end up with a smaller view, a smaller amount. So this function is going to approach 0, but it's never actually going to touch it. And that becomes a limit on our range. So our range, again in set notation, set of all y such that y is an element of real numbers. Again, real numbers here because we have a continuous line, but y will always need to be greater than, but not equal to, because it will never hit 0, but it's going to be greater than 0. So that is our range. The x-intercept by logic of the fact that it never touches 0, there will not be an x-intercept. It's going to get closer as we head to negative x infinity. It's going to get closer and closer and closer to 0, but it will never actually touch it. The y-intercept, as we saw when we first observed the graph, is 0.01, which happens to be common to all of them. So growth or decay is the next thing I'd like to look at. So we can look at this visually from the graph. We see that as we read the graph sort of from left to right, our function is increasing. So visually from the graph, you can tell it's growth because it's going up as you read left to right. We can also know that because our, let's get the highlighter, because our base is going to be 2. So it's a base larger than 1. So that is going to be growth. And the next thing I'd like us to look at is what is the behavior of our function as x heads towards positive infinity. So as I was saying, when you've got this graph and it's heading off to positive infinity, like this direction here, what is the tendency of our graph? What value is it approaching? And we would say, as we talked about, that as x approaches positive infinity, y approaches, let's make that look a bit more like an arrow, y approaches positive infinity. Gosh, that is not a great infinity sign. That is not better, but I'm going to leave it. Again, meaning that it's going to keep going up, it's going to double, it's going to reach as high as you can possibly imagine, and then double again. As it heads towards negative infinity, however, as we talked about, that value is going to approach but never touch 0. So it's going to be approaching 0 as we head off in the negative direction. Now the asymptote, this is sort of new word for us, or a new word for us. An asymptote is a value that our function approaches but never touches. It represents sort of like a dead zone in our graph, or visualization of it. Oh, I already have, let's do hot pink, I guess. So our asymptote, in this case, would be 0. It's something that our function approaches but never quite touches. Y equal to 0 is going to be the value that our graph gets close to as it heads off to negative infinity but never touches. And that is going to be the last value that we fill in here. The asymptote, again, written like an equation, it's like an axis, y equals 0. So there's our first graph worked out in terms of some of the characteristics that we've been looking at over the semester. Let's look at g at x next. So g at x is going to be the green one. So maybe I'll take a second, just tidy things up here a little bit if I can, without erasing a whole bunch of stuff. Oh, I erased a little bit of stuff. Ah, well, it's not the end of it. Okay, so let's change up here to green. So again, we've got g at x equals 3x, and again, it's actually very similar to the f at x in that it has a y-intercept at 1, which we can see right there. And as we head off to positive infinity, our graph is going to be tripling each time. So you've got 1, 3, 9, 27, 81. It's going up more quickly, but it's still tripling each time. And as we head off in the negative x direction, you've got 1/3, 1/9, 1/27, 1/81, etc. So it's going to be getting smaller, but again, it will never actually touch 0. It will never get there. So let's start filling it in. Oh, I also should point out this pattern continues as well, where outside of the y-intercept you have 3 and 1/3, 9 and 1/9, next would be 27 and 1/27. That's a pattern that will continue. So our domain, again, is going to be wide open. That thing's just going to keep going. So the set of all x, such that x is an element of real numbers. No problem there. Our domain, again, or rather our range, limited by the fact that it will never actually get to 0. So the set of all y, such that y is an element of real numbers, where y is greater than 0. Never going to, not equal to, it's never going to reach 0, but it will be greater than 0. In terms of our x-intercepts, by virtue of the fact that it never crosses or touches the x-axis, there will be none of them. Our y-intercept, 0, 1, as we saw when we looked at the graph. Our behavior as we head off toward, or sorry, let's look at growth or decay first. So as we read our graph left to right, it's going up. Our b value is 3, so this is also going to be growth. Our end behavior, as we head off towards positive x, our thing is just going to continue to approach positive infinity. And as we head towards negative x values in infinity, our graph is going to approach but never touch 0. And our asymptote is going to be the same. What value will our function approach but never touch? Also 0. All right, there's g at x. Let's change up our colors and let's go and have a look at the last graph we have put in here, which is f at x, or h at x rather, equals 1/2 x. So there it is. Again, we've got ourselves a y-intercept at 1. Now, what's interesting is as our function heads off towards negative infinity this time, our graph is going to be doing that sort of escalation. It goes from 2 to 4, next will be 8, 16, 32, 64. In a lot of ways, it's actually a mirror, a horizontal reflection of f at x equals 2 to the exponent x. And we see as we head off towards positive infinity, we get that 1/2, 1/4, 1/8, 1/16, etc. It's going to approach but never actually touch 0. So a lot of the components of this are going to be the same. So let's have a quick look at the patterning first. Patterning in our table outside of our y-intercept, it's the inverse of what it was before. So instead of there being whole numbers that are doubling as we increase through positive x values, the inverse is happening, where those positive values are showing up for our negative values. Okay, so let's start filling some things in here. Our domain hasn't changed. Sure, it's sort of a mirror of itself, but it is going to still go out to infinity in both directions. So we still have the set of all x such that x is an element of real numbers. No limits. Our range is still going to be limited by the fact that it will approach but never touch 0. So the set of all y such that y is an element of real numbers where y is greater than 0 but not equal to. It's never going to touch it. Any x-intercepts, well, it doesn't ever get to the value of 0, so there will be no x-intercepts. Our y-intercept is 0, 1, of course. Now, growth or decay, as we read our graph left to right, we see that our graph is actually shrinking or getting smaller as we go left to right, and that will be decay. We can also identify that by it having a b value of 1/2 right there. So let's find it. There we go. So this is going to be decay. And let's consider our end behavior. So as we head out to positive x values, this time we're actually going to see y approaching 0. Again, it's a mirror of what we saw before. And when we head out to negative infinity, y will be approaching positive infinity, meaning our graph is going to be going up 2, 4, 8, 16, 32, etc., all the way as high as you can go and then double it again. And our asymptote, despite the fact that it's reflected compared to 2 to the exponent x, our asymptote also stays the same. It's going to be y equals 0. It's important to write that as an equation since, as I said earlier, it acts like an axis. So there's the first page of our note. I'm going to come back and we're going to work through some comparisons quickly, and that's going to finish up our lesson. So we'll see you in part 2.